Okay. All right, so just a quick note. Oh no. There you go. So October 12, 2021. Note on expected value. Okay, so just very briefly, this isn't an overly taxing mathematical what's the word, relationship, but we would have the expected value operator E of X is a linear operator. Okay, so basically all this means is so for example, let A Y, let X equal A times Y. Okay, so X is a random variable Y is a random variable and A is a constant. Okay. For example, A equals 2. Okay, so little a in this situation is just a number. It's like just any real number. So 2, 3, 4, whatever. Okay. So then the expected value of X is equal to the expected value of A times Y is equal to A times the expected value of Y. So the point is, when you multiply a random variable by some number, the expected value of that product is just that number multiplied by the expected value. Similarly, if we let, for example, X equal, let's say Y minus little a, then the expected value of X is equal to the expected value of Y minus a, which is equal to the expected value of Y minus little a. So the point of this, of these examples, is to illustrate that if we wanted to, so suppose that we have the expected value of some random variable. So for example, on assignment number 2, we have the expected value of X because that's what we have to find in question 4A. If we want to find the expected value of some other random variable that's a function of X. So for example, on assignment 2 in 4B, I believe we have the expected value of Y is equal to X minus 1, or we have Y equals X minus 1. What is the expected value of Y? Well, all we have to do in that situation is substitute in. So we can say, kind of like what we did in this short definition here, that the expected value of Y is equal to the expected value of X minus 1. And then we know that the expected value of any random variable minus a constant is just the expected value of that variable minus that constant. Okay, so the point of this is just to illustrate that in that particular problem, because of the properties of the expected value operator, that particular solution just works out to being the difference between the expected value and 1. Okay, not my best explanation. This so this stuff is usually not aren't things that we teach until the second year, but that's the idea. Oh, I didn't know that. Okay, any questions? It would be the same answer if you wanted to redo the whole problem that way, but you're just subtracting a constant out. So you would end up, it would be the same answer if you wanted to like plug x minus 1 into each of the parts. That would result in the same thing. Yeah. Yeah. So that would give you the same solution, but it's a lot, it's much longer to do it that way because you have to redo all of part 4a with the minus 1 in each of the different parts. Yeah. And you should end up at the exact same thing. Like if you just try this and compare it, they should be identical. Oh, sorry. And then for the people online, the question, so the question was, so what I just explained is not the same answer as calculating each part of expected value of y using the formula. In the same way we found expected value of x, and they are the same. So you can take x minus 1 and basically just plug it into the expected value formula, and you would end up with the same solution if you approach the problem in that way. It's just a bit longer because you have to redo the calculation from part A, which maybe in hindsight was the point of the question. And now I'm just giving the trick doing it fast, but yeah, the more you know, right? Any other questions? Okay. All right, so no, a negative expected value is perfectly reasonable. Expected values being negative, like again, in the context of gambling, for example, if you have a negative expected value, that's basically indicating that over the more that you play, the more likely it is that you're actually going to lose money. It's just saying that the overall outcome or the overall average return on this particular experiment is negative. So if you're measuring value in terms of dollar value, it would imply that you're going to lose money in the long run, which is typically why if you go gambling and you win early, you should just leave. Jordan knows. All right. Any other questions? Okay, so what we're going to do for the remainder of today's lecture is work through the rest of lecture set 4. The remainder of lecture set 4 is really about the binomial distribution, how to work with what is called the binomial probability formula, and the properties of a binomial random variable. And when I say properties, I mean the expected value and variance of a binomial random variable. So to set that up, we start by defining formally what is called a repeated trial. So this particular definition is fairly easy to understand. It's basically saying, suppose that you have an experiment and you perform the experiment once. We can think of that as a trial. So let's say, like in a very simple context, that your experiment is rolling 2 die. So you roll the 2 die one time, you've now performed a trial. Then let's say that you repeat that and you roll the die again, you've now performed 2 trials. And then let's say that you roll them again, you've now performed 3 trials. And then let's say that you roll 2 die 50 times, you've now performed 50 trials. Okay, so the definition of a trial is basically one outcome from the experiment, or performing the experiment one time. Right. The simplest possible trial is what is called a Bernoulli trial. A Bernoulli trial is an experiment where you only have 2 outcomes, success or failure. And what's important about the success and the failure is that they are complements. So a Bernoulli outcome or a Bernoulli trial is an experiment where you perform some action and you either get a yes or a no, or you get this thing or its complement. So an example of a Bernoulli trial, and again, this is one trial, so one action from the experiment. So an example of a Bernoulli trial would be flipping a coin. That's probably the most general and basic illustration of what a Bernoulli is. A coin by design has 2 outcomes, heads or tails, or whatever the faces on the coin are. And those are complementary events. So the probability of getting a head is the 1 minus the probability of getting a tail. All right. Now there's a lot of different situations where we can set up Bernoulli trials. A lot of the time it requires a little bit of manipulation or a bit of an understanding of how it could be a success failure. But for example, a multiple choice question on a test, one question, is typically a Bernoulli. The reason it's a Bernoulli is because even if you have 5 different options, there's only one correct option. So if your multiple choice test has 5 outcomes, you have a 20% chance of getting it right and an 80% chance of getting it wrong, assuming that you know nothing about the material. If you've actually studied, your probability of getting it right would go up. But assuming that you know nothing and it's a random guess, it's a 20% chance of getting it right, 80% chance of getting it wrong, and that would again be a Bernoulli trial. So the most important thing to take away from this is that the Bernoulli is one action where the outcome is a success or a failure, and those are complementary events. So there's only 2 outcomes in the sample space. All right, now where the binomial distribution comes into play is on its own, the Bernoulli trial is not overly interesting, right? So we flip a coin one time. We know that for most coins, it's going to be a 50-50 chance of getting a head or a tail. But what if we repeat the Bernoulli experiment multiple times? So let's say we flipped 10 coins. Now the problem becomes a little bit more interesting. We might ask, for example, if I flip a coin 10 times, what is the probability that I get 7 heads? Or what is the probability that I get only 1 head? Or what is the probability I get 4 tails? All of these outcomes are substantially more complicated because we have now repeated the experiment. And what makes it more complicated is that there are many different ways that you can arrive at those particular counts of heads or tails. So what I mean is, if I flip a coin 10 times and I want to know the probability of getting 4 tails, one way that this can happen is the first 4 flips are tails and the last 6 flips are heads. But I could also have the situation where the first 6 flips are heads and the last 4 flips are tails. And then I could have any combination in between. So there are many different combinations of outcomes that can reveal what we are interested in. So what the binomial distribution allows us to do is effectively account for all of these different combinations of outcomes such that we can compute the probability of observing some number of outcomes of interest within n Bernoulli trials. Now, There's a few things that have to hold true in order for us to use the binomial distribution. One, every single trial has to be exactly the same. So you can't mix different types of Bernoulli trials together within the experiment. If you're interested in coin flipping, you have to repeat the coin flip with the same coin as many times as the experiment requires. Every single flip has to be independent, or every single Bernoulli trial has to be independent of the one that succeeds it and came before it. Okay, so all trials are independent. And every single trial has to have the same probability of success and the same probability of failure, which follows from my first point. All right. So when we perform multiple Bernoulli trials, we can actually think of the outcome as being a count of the number of successes across the trials. So we can think of, for each trial, a success being a 1 and a 0 being and a failure being a 0. The point of this is that it basically just allows us to add together the number of successes. Okay, so for example, okay, let's suppose that we flip a coin 10 times. So, one sec. I don't know why I spaced this out so much. All right. So let's suppose that we flip a coin 10 times. One of the possible outcomes might be head, head, tail, tail, heads, tails, heads, heads, tails, heads, right? If we mark a head as a success and a tail as a failure, then we can also think of this outcome as being 1, 1, 0, 0, 1, 0, 1, 1, 0, 1. Okay. So what that means is we observed 1 plus 1 is 2, plus 1 is 3, plus 1 is 4, plus 1 is 5, plus 1 is 6, 6 heads. So then the question becomes, what is the actual probability of observing 6 heads across 10 flips? Well, this is only one of the ways that we could achieve that result. There are actually 10 choose 6 different ways that we can arrive at this outcome. So what we have to be able to do when we're interested in computing the probability of observing an outcome like the one shown below across n Bernoulli trials is account for all the different combinations that can lead to what we are interested in observing. Okay, so to further illustrate this idea, consider an experiment or a test where you have 5 multiple choice questions. Now, in this particular situation, suppose that you are taking the test, this 5 multiple choice question test, and this particular test is some sort of test where you would have 0 idea of what's going on. So you're basically taking this test and you're just guessing randomly at each answer. Given that you are guessing randomly what the answer to each question would be, we can assign a probability of success of 20%. So there's 5 outcomes per multiple choice question. Therefore, there's a 20% chance that you get the question right. And then we can assign an 80% chance that you get the question wrong because there's 4 different answers that would lead to the wrong solution. So the question then becomes, how many ways can we get 4 questions correct? Okay, well, following from the previous illustration, you can see that there's actually 5 different ways that this can happen. For example, we could get the first 4 questions correct and the last question wrong. Or we could get the first 3 questions correct, the 4th question wrong, and the last question correct. In this case, I have capital R meaning right, so right is correct. Another situation is we could get the first two right, the third one wrong, and the last two right. The fourth outcome would be the first one right, the second wrong, and the next three right. And then the last outcome would be the first answer wrong and the last four right. Okay, so it turns out that there's 5 different ways that we can get 4 questions correct out of the 5 questions that we are answering. And that is, to Michael's question, a combination. So in order to count the number of successes across n Bernoulli trials, we use the combinations rule. Okay. All right. Oh, sorry, to Michael's question. Yeah, we use, so the question is, why do we use a combination here rather than a permutation? It's because the order, well, the order doesn't matter in this situation. Okay, so we're using a combination to count the number of just thinking here. Yeah. Okay, well, let's just enumerate this really quickly here. So we have 5C4, 5 factorial over 4 factorial, 5 minus 1 factorial. Which is equal to 5 factorial, 4 factorial, 4 factorial. And then 5P4 would be 5 factorial, 5 minus 1 factorial, which is 5 factorial over 4 factorial. Ooh, this isn't a good illustration actually, because these are going to be very similar. Oh, it's because I don't know how to multiply or subtract, that's why. There we go, 1 factorial. So this is 5 over 1 equals 5. And this would be 5 times 4 times 3 times 2, which is 20, 60, 120. Okay, so then there's 120 different outcomes. And what would these outcomes look like? So you would have, oh yeah, okay, so this is why it doesn't matter. Okay, so like for example here, with the first outcome, what this is basically saying to you is you have Q1 right. I need to label. So this is going to be like Q1 right, Q1, Q2, Q3. Damn it. Okay, sorry, 1 second. We don't remember the room. Okay, so we have Q1, Q2, Q3, Q4, Q5. Okay, so this is basically saying right, 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 wrong. If you were to take the permutation would return, for example, okay, I got Q2, Q3, Q1, Q4, Q5. Right, 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 wrong. But these things are exactly the same solution. So counting that order, like the order in which you got the questions right, doesn't make a difference because it's the same outcome in terms of which questions you actually got correct. Okay, yeah, so that makes sense, I guess. Yeah, cool. No one's ever asked me that before. I had to think about that for a second. So I was like, anyways, all right. Cool. Any other questions? No, don't use the permutation, because the permutation is saying, like, the permutation would be counting the order in which you answer the question, but that doesn't matter in terms of the solution. What matters is which questions you get correct. So we only need to use a combination because we don't care about the order in which you get them correct. We just care about which ones you get correct. Does that make sense? Yeah. As it's written on the slide, it's correct. It's a combination. Any other questions? All right, so say that we conduct n Bernoulli trials and we want to know the probability of getting some number of those, we want to know the probability of getting some number of successes, which we typically call little x, out of those n Bernoulli trials. So we saw on the previous slide that if you have, for example, 5 Bernoulli trials and you want to get 4 successes, there are 5 choose 4 different ways of observing that outcome. Now, if we want to compute the probability of X successes out of n Bernoulli trials, we have to account for each of the different ways that we can observe that outcome. All right, so to illustrate this, how this would work from a fundamental point of view, I'm going to use what's called a tree diagram. Now I'm going to simplify the experiment because the diagram is going to get very, very big if we use the 5 choose 4 example from the previous slide. So let's suppose that instead of having 5 questions, we only have 3 questions. And out of the 3 questions, we want to get 2 correct. All right. So how would we find the probability of this? Okay, so first we can say P correct is equal to 0.2, and we can say P wrong is equal to 0.8. So again, for each question, we have a 20% chance of getting it right and an 80% chance of getting it wrong. The assumption again here is that you know nothing about the material. If you start studying for the test, it's going to change these probabilities per question, and it's no longer binomial. But this, so we're assuming that you know nothing about the material and you're guessing. Okay, so we want to know the probability of getting 2 out of 3 questions correct. So the way that we can figure this out is, again, we can use what's called a tree diagram. So a tree diagram looks like this. So this is going to be Q1. Okay. Then we're going to have Q2. And then we're going to have Q3. Okay, so what happens here? On Q1, we have 2 paths. To get to Q2, we can either get the question right, or we can get the question wrong. Okay, so if we go along the branch of being right, this comes with a 20% chance. And if we go along the branch of being incorrect, that comes with an 80% chance. Okay, then from here to here, we can either be right or we can be wrong. And then from here to here, we can either be right or we can be wrong. Okay, and again, this is a 0.2, 0.8, 0.2, 0.8. Okay, and then from Q3, we have the same outcomes again. So we can be right or wrong. Right, so right, wrong, right, wrong, right, wrong. And each of these come with the same probabilities. Okay. I don't know why I drew the branches so big. Scaling issues. Okay, so what the tree diagram is showing us are all the different paths that we can take along the test. Like, for example, if you follow the upper branches, you can see that you have 3 rights here. So this is all 3 questions correct, which we're not interested in. If you follow the next branch, you go right, right, wrong. Then you go right, wrong, right, right, wrong, 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 right, right, wrong, right, wrong, 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 right, wrong, wrong, wrong. Okay, so we are interested in this outcome, and this outcome, because we want to know the probability of getting 2 out of 3 questions correct. Okay. So the next part of this is to basically just apply the probability rules that we studied in lecture set number 3. So we can see here, or we know, because we are guessing randomly on each question, that each question is independent. So the probability of success never changes from question to question. So for example, the probability of being right, right. So the probability of being right, right, wrong is equal to 0.2 times 0.2 times 0.8, right? And that's just independence rule. Actually, just for clarity, we can think of right, right, wrong as an intersection of the 3 events. So this is, because of independence, probability right, probability right, probability wrong. Okay. And that gives us 0.032. And then we can see for the next event, this is going to be 0.2 times 0.8 times 0.2, which is the same thing. And then this is going to be 0.8 times 0.2 times 0.2, which is the same thing. All right, so one thing that we've observed here is that the outcome that we're interested in, regardless of the way that we get to it, have the exact same probabilities. So therefore, it's easy to show that the probability of getting 2 right is equal to 3 times 0.032, which is 0.096. Okay. Now, the other part of this is to recognize that the way that we get the 3 would then be by the combination rule. So if we were to ask, or if we were to compute 3 choose 2, this is actually equal to 3. So basically, we can take the probability of one of the outcomes of interest in any of the different scenarios that we need to arrive at it, and multiply that by all the ways of achieving that outcome of interest. which we can count using the combinations rule. And that will give us the probability of X successes across N Bernoulli trials. Okay, so that on its own might be a little bit confusing to take in. So before stopping for questions, let me just show you how the binomial probability formula works in relation to this experiment. And that might help clear up any confusion that you're experiencing at this particular moment. Again, our goal is to count or to find is a better word, the probability of observing X successes across little n Bernoulli trials. All right. So to find the probability of interest, we use what is called the binomial probability formula. Essentially, if we have n Bernoulli trials, then the number of successes X across those n Bernoulli trials, is a binomial random variable. So the binomial distribution models the number of successes across n Bernoulli trials. That's the purpose of this distribution. So a Bernoulli models one trial with a success-failure outcome. The binomial models X successes across little n Bernoulli trials. So they're intrinsically linked, but they are different. Now, for our purposes, one of the main or most important results for a binomial random variable is the probability formula, which is given in equation 1. What this formula allows us to do is compute the probability of observing X successes across little n Bernoulli trials. Here, we assume that little p is the probability of success on each Bernoulli trial. And little p has to be constant. So each of the Bernoulli trials have to be independent in order for this formula to be valid. You can see that the way this formula works is you start with this operator here, which typically confuses students because of the notation, but this is just NCX. Okay, so this is another expression for the combination rule. So this is basically NCX multiplied by little p to the power of X multiplied by 1 minus p to the n minus X. I'm going to use a dot for multiplication so it doesn't get confusing. Okay, so this is multiplied by. Right? And if you're following along, you can see that basically all this formula does is it generalizes the result from the tree diagram that we showed above. It's just saying, take the probability of success, put it to the power of the number of successes, take the probability of failure, put it to the power of the number of failures, multiply those together, and then multiply that by all the ways of observing X successes across n Bernoulli trials. Okay, so this formula here is just a general formula that allows us to arrive at the conclusion to a tree diagram like the one shown on slide 17 without actually having to draw the diagram out every time. And you can imagine that this is very helpful to us, particularly in situations where we might have like 100 trials or some really large number of trials, and drawing that diagram out would be practically impossible. Yeah, Jordan, this is the question that we used for number 6 on assignment 2. That is correct. Okay, any other questions? No, you don't need it for 4C. Technically, 4C is a subset of this. So actually, I guess you could use it there, but you don't need to. Yeah, it's probably easier not to, but you could do it. All right, so let's go through some examples showing kind of the common situations where we use this formula. Okay, so the first example, I'm using drawing cards from a deck with replacement. So when we draw cards from a standard deck with replacement, we create a series of independent events. So the with replacement aspect here is crucial to making each of the trials Bernoulli. If you weren't replacing the card, you would, if you were not replacing the card, you would then change the probabilities of success on each external outcome. And that would make the probability of success not constant, and it would make the trials dependent. So we have to use replacement here in order for the trials to be independent and have the same probabilities of success. Okay, so we are going to draw a card from a standard deck 8 times with replacement. And we want to know the probability of observing 2 clubs. So we're basically saying, let club be a success and let any other type of card be a failure. So in this situation, we would have little n is equal to 8 because we have 8 draws from the deck. So we're performing the experiment 8 times. We would have little x equal to 2 because we have 2 successes, which would be 2 clubs. And then little p is the probability of observing the club. So there's 13 clubs in the deck, 52 cards total. So little p is 13 over 52, which is a quarter. Now, all we have left to do is plug in to the formula for the probability of x. So the binomial probability formula. So we have the probability that x is equal to 2 is equal to 8 choose 2. So as a reminder, again, this here is just another way of writing 8 choose 2. Okay, so this is the combinations rule, not division. So we have 8 choose 2 times 1 over 4 to the 2 times 1 minus 1 over 4 to the 8 minus 2. From this point, we're just solving for the values of interest, right? So 8 choose 2 is equal to 28. Okay, 0.25 to the 2 is equal to 0.0625. And 0.75 to the 6 is 0.1779785. You multiply those together, and here's your probability of getting 2 clubs across 8 draws from a deck with replacement. So the actual application of the formula is pretty straightforward. It's really just plugging in. The only tricky parts are identifying the probability of success for each trial, and I suppose identifying n and little x, but those will typically, n in particular is typically very clear because it'll say, like, imagine you answered 100 multiple choice questions or something like that. N is just the total number of times you conduct the experiment. Okay, so let's look at another example now. I have quite a few examples for the binomial. Suppose that the probability that a driver gets caught speeding at the corner of 104 Ave and 105 Street is 0.89. What is the probability that 17 out of 20 drivers will not get caught speeding? Okay, so we're going to say little n is equal to 20. Okay, so we have 20 different drivers of interest to us going through this intersection. Little x is equal to 17. So we want to know the probability of 17 out of 20 drivers not getting caught. And then little p, which is the probability of not getting caught is equal to 0.89. Okay. All right, so from this point, all we actually have to do is sub in. So we have the probability x equals little x is equal to n choose x, p to the x, 1 minus p to the n minus x. So this is 20 choose 17, 0.89 to the 17, 1 minus 0.89 to the 20 minus 17. All right. So if we simplify this a little bit, we would have 20 choose 17, 0.89 to the 17, 0.11 to the 3, and that gives us 0.209. Any questions? Okay, so the next exercise is still a binomial problem, but we are now considering multiple outcomes within the experiment. So this one says, suppose that an experiment consists of drawing a single card from a deck 8 times with replacement. So this is actually an extension of the first example. What is the probability we observe at most one club? So the language here is very important. So we have little n is equal to 8. We're going to have little p is 13 over 52, which is 0.25. Okay. Now, x in this case can be at most 1. So there's actually 2 different outcomes for x. X could be 0, so no clubs, or x could be 1 club. So we are interested in both. So in this experiment, we are interested in the probability that x is less than or equal to 1. Okay, which is equal to the probability that x equals 0 plus the probability that x equals 1. Okay. Now, all we're doing is applying the binomial formula for x is 0 and x is 1. So we're going to have 8 choose 0, 0.25 to the 0, 1 minus 0.25 to the 8 minus 0, plus 8 choose 1, 0.25 to the 1, 1 minus 0.25 to the 8 minus 1. Okay, so a couple quick things here. Anytime you have a value choose 0, that's going to be equal to 1. So 8 choose 0 is 1, 10 choose 0 is 1. In general, anything choose 0 is 1. Because there's only one way of getting nothing, of choosing none of the outcomes of interest out of the total number of events. 0.25, anything to the power of 0 is also 1. Why did I choose 0? So the question asks, what is the probability we observe at most 1 club? So at most 1 means less than or equal to 1. So there's only 2 events that correspond to being less than or equal to 1. X is equal to 0 and X is equal to 1. So we can observe no clubs or we can observe 1 club. Okay, so anything choose 0 is 1. Anything to the power of 0 is 1. And then we have 0.75 to the 8. Okay, and then we have 8 choose 1. Anything choose 1 is that value. So this is going to be 8 times 0.25 times 0.75 to the 7. Okay. All right, so then this gives us 0.1001129 plus 0.2669678, which is equal to 0.367. Okay. Exercise 3. Okay. Brittany, how are you getting the second last line? This line? So 0.1001129. That's 1 times 1 times 0.75 to the 8. And then 0.2669678. That's 8 times 0.25 times 0.75 to the 7. This means multiply. Make sense? Okay. Jessica, yeah, 3 decimal places for the final answer is always sufficient. Number 3. An experiment consists of drawing a single card from a deck 8 times with replacement. What is the probability we observe at least 2 clubs? Okay, so we have little n is equal to 8. P is equal to 0.25. Now, what is x going to be? Okay, so x is at least 2. So this can be 2, 3, 4, 5, 6, 7, or 8. Okay, so this is a bit more of a nuisance, right? Because we know from the previous example that one of the ways that we can do this is going to be x is equal to 2 plus x is equal to 3 plus x is equal to 4 plus x is equal to 5 plus x is equal to 6 plus x is equal to 7 plus x is equal to 8. Okay. So we can do it this way, and we can just compute the binomial probability formula 7 times. So 1 for each of the different values of x that I've written out. This is a fairly tedious approach. The other thing that we can do is recognize that the probability that x is greater than or equal to 2 is 1 minus the probability that x is less than 2, right? And then this is our complementation rule. Okay, now the value of this is we now have the probability that x is less than or equal to 1. Okay, so x being strictly less than 2 is the same thing as x being less than or equal to 1. Those are equivalent. Okay, and now this thing is simply x equals 0 plus x is equal to 1. In red, I wrote complementation rule. This is just the complement. Min, if it was 2 clubs, x less than or equal to 2, so what you wrote there is correct. Yeah, x less than or equal to 2 is x equals 0 plus x equals 1 plus x equals 2. Yeah. All right, now this result here, we actually worked this out in the previous example. So this is going to just be 1 minus 0.367, which is equal to 0.633. Okay, another example. The probability that a carton of eggs has a broken egg is 5%. If 10 cartons are purchased, what is the probability at least one has a broken egg? Okay, so this is a classic binomial problem, and the language here is very important. So here we have probability at least one. This is the type of problem that comes up very often when quizzing students on the binomial distribution. So there's a trick to this. First, let's write down what we know. So we have 10 cartons. The probability of one broken egg, which we're going to call little p, is 0.05. Okay. All right. Now, we want to know the probability at least one is broken. So we want the probability that x is greater than or equal to 1, which in this case is going to be x equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, now in writing it out this way, what we have determined here is that our probability of interest, which is the probability that x is greater than or equal to 1, so that's at least 1, is p x equals 1, 2 p x equals 10. Okay, so again, this is, you can do it this way. There's nothing wrong with this. It's just very long. The trick here is to recognize that this is actually equivalent to the probability that x is strictly less than 1, which is equivalent to the probability x is equal to 0. So whenever we're asked for the probability that at least one, whenever we are asked for the probability of at least one success, that's the same thing as 1 minus the probability of no successes. So this is going to be 1 minus 10 choose 0, 0.05 to the 0. Sorry. I guess I can just do it like this. 1 minus 0.05 to the 10 minus 0. Okay. So this is 1 minus 1 times 1 times 0.95 to the 10, which is 0.402. All right. So much binomial. Any questions? Cool. Okay, the last thing I want to talk about in regard to a binomial random variable are the properties of that random variable. So the question is, why do we calculate for x equals 0 and not x equals 0 and 1? So we are finding the probability that x is strictly less than 1. Strictly less than 1 means x equal to 0. So being equal to 1 would not be included here. If you compare this to what we had on slide 21, here I had x less than or equal to 1. So less than or equal to includes. So that equal sign means represents a different outcome. Okay, the last thing I want to talk about are the properties of a binomial random variable. Well, the last thing from lecture set 4. We learned how to calculate the expected value of x and the variance of x for a discrete random variable. Okay, so those were those formula that we utilized back on slide here on slide 9 and slide 10. So when we have a discrete random variable, in the general case, we have to compute expected value using the sum of x times p of x and the variance using either the defining or the computing formula. When we have a binomial random variable and we want to find its expected value and its variance, we don't have to plug into that formula because the expected value and the variance of a binomial random variable are known and they're very easy to compute. So if we want the expected value of a binomial random variable or the mean of a binomial random variable, which again are the same thing, we simply take the number of trials and multiply by the probability of success. If we want the variance or the standard deviation via variance of the binomial random variable, we take number of trials multiplied by p multiplied by 1 minus p. Okay, so suppose we draw 20 cards from a standard deck with replacement. Okay, so we're just doing our deck experiment again, but we're drawing more cards this time. So we have little n is equal to 20. How many face cards would we expect to observe? So we're asked for the expected value of x, where x counts the number of face cards. All right, so the probability of observing a face card, which is the same thing as little p in this case. So the probability of success on each draw from the deck is going to be the number of face cards in the deck divided by the total number of cards in the deck. So there's 4 suits in a standard deck of cards: heart, diamond, spade, club. Each suit has 3 face cards: jack, queen, king. So there are a total of 12, 3 times 4 face cards in the deck. So that gives us 12 over 52, which is 6 over 26, which is 3 over 13. Right? So to find the expected number of face cards, no, it's far more complicated. If you are finding, it's not with replacement either, right? So totally different scenario. And it's illegal, don't do it. So if we wanted to find the expected number of face cards, we're gonna say the expected value of X is equal to little n times P, which is equal to 20 times 3/13, which is equal to 4.615. Right? So if we were to repeat the experiment of drawing 20 cards with replacement a very large number of times, we would converge to about 4.6 face cards across all of those repetitions of this experiment. Okay. All right, in part B, it says, what is the standard deviation of X, which counts the number of face cards observed? Okay, so the standard deviation of X is equal to the square root of the variance of X, which is equal to the square root of n times P times 1 minus P. Okay, so this is going to be 20 times 3/13 times 1 minus 3/13, which is going to be the square root of 3.550296, which is 1.884. All right. Any questions? One more example. Okay. Or exercise, one more exercise. Okay, so the probability that a woman gives birth to a girl is 0.5. If a woman gives birth to six children, calculate the probability she gave birth to at least 3 girls, the expected number of boys, the variance of X, which counts the number of girls she gave birth to. Okay, so we have little n equals 6. So we have 6 children to consider. So we're considering each pregnancy and subsequent birth a trial in this case. The probability that we have a girl is equal to little p, which is 0.5. Well, the probability that she had a girl. And then we want to know the probability she gave birth to at least 3 girls. Okay, so X at least 3 is greater than or equal to 3. So this is X equals 3, 4, 5, 6. Okay, so what we have here is the probability X is greater than or equal to 3, which is the probability X equals 3 plus the probability X equals 4 plus the probability X equals 5 plus the probability X equals 6. All right, at this point, we don't really have a lot of options. We basically just have to plug into our binomial probability formula. You could, if you wanted to, say, all right, well, this is 1 minus the probability X is less than 3, which is 1 minus the probability X equals 0, plus X equals 1, plus X equals 2. And in this situation, you can do X equals 0, X equals 1, X equals 2 in the binomial probability formula and subtract from 1. But in terms of the overall number of steps, you're not actually saving that much time. So I would say that both of these options, written in black or written in red, pretty much the same in terms of a total commitment of time to the problem. So we'll just follow the first option. So we're going to have 6 choose 3, 0.5 to the 3, 1 minus 0.5 to the 6 minus 3. Plus 6 choose 4, 0.5 to the 4, 1 minus 0.5 to the 6 minus 4. Plus 6 choose 5, 0.5 to the 5, 1 minus 0.5 to the 6 minus 5. Plus 6 choose 6, 0.5 to the 6, 1 minus 0.5 to the 6 minus 6. All right, okay. All of these are going to be evaluated in the same way that we've been practicing throughout this lecture set. So you should be able to show that this is going to give you the following, which is 0.657. Okay, so the probability of at least 3 girls out of 6 children with a consistent probability of having a girl being 0.5 is 0.657. Okay, in part B, it asks, what is the expected number of boys? All right, so here we have the expected value of X is equal to little n times P. Okay, in this case, X is counting the number of boys. So P, which is the probability of a boy, is going to be 1 minus the probability of a girl, which is 0.5. Okay, so therefore, the expected value of X is equal to 6 times 0.5, which is 3. All right. And in this case, we have a very nice interpretation. We're basically saying if you have 6 children and the probability of having a boy or girl is 50% on each pregnancy, then the expected number of children or boys is going to be 3, and the expected number of girls is going to be 3. Okay, last problem. I'm kind of running out of gas. So the variance of X, which counts the number of girls she had. So we have sigma squared X is equal to N times P times 1 minus P. This is going to be 6 times 0.5 times 1 minus 0.5, which is 1.5. We did it. Oh, good job to you for hanging in there. All right, now we can finish assignment 2. So all of these exercises we did today on binomial, that's for question 6. So lots of examples to help with that question. I'm going to have extended office hours today. So I think I'm going from 12:45 to 3:15 in the same link. So we didn't have office hours yesterday because of Thanksgiving. So just long extra today. If you have questions, feel free to stop by. And there's only 5 minutes left. So I'm not going to start lecture set 5, but if anyone has any questions, about the assignment or the material, I'll hang around for the next 5-10 minutes. And then, of course, office hours will be available. So for those of you that have had enough, you're free to go. And for those of you that have questions, you are free to ask.